Chloride. The initial part will be discussing three compounds that contains halogen. Okay, the first one, halogenoarine. Then you have your halogenoalkane, and of course the last part you have your acid chloride or can be acid bromide. For discussion, we're going to specifically look at chlorobenzene, alkyl chloride, and as well as acid chloride. The first thing to study is the strength of the bond energy between the carbon versus that of the Cl. In this case, you will find that the C to Cl bond in halogenoarine or chlorobenzene is the highest, primarily because the lone pair electron of your chlorine overlap with the delocalized pi electrons in benzene, resulting in partial double covalent bond. So we'll now take a look at the bond energy between the C to Cl. In this case, the C to the Cl here, C to the Cl bond, and as well as the C to the Cl bond here. And we do note that the C to Cl bond in your chlorobenzene is the highest, given the fact that the lone pair electron of chlorine overlap with the delocalized pi electrons in benzene, resulting in partial double covalent bond between the C and Cl. So this is in actual fact the strongest. If it has the strongest bond, then therefore you will find that it's very difficult for it to undertake any nucleophilic substitution, and hence it does not undertake any hydrolysis reaction with water molecules. Now we'll compare your chloroalkane and your acid chloride. In the case of acid chloride, it's important to note that the C double bond O is in fact an electron withdrawing group. So in the case of acid chloride, you know that you have a C double bond O. The C double bond O is an electron withdrawing group. So the presence of the electron withdrawing group weakly polarizes the C to Cl bond. What does it mean? It means that it is actually fighting against the electronegativity of your chlorine, because C double bond O, like chlorine, are both electron withdrawing. Hence, the shared pair electron that's here, that's in between the C to Cl, is less polarized. If it is less polarized, then the Cl here is a smaller delta minus, and the carbon here is a smaller delta plus. Conversely, in the case of CH2Cl, you will find that the chlorine is the only electronegative atom relative to C and H. Therefore, because of that, it will pull the shared pair electron towards itself, resulting in Cl being more delta minus and C being more delta plus. Hence, because of this, we will say the presence of electron-releasing alkyl group strongly polarizes the C to Cl bond, resulting in a strong bond energy. Relative that to actually acid chloride, where the presence of electron-withdrawing carbonyl group weakly polarized the C to Cl bond, resulting in a weaker bond energy. And in conclusion, that explains why halogenoarine does not undertake hydrolysis reaction with water molecules, which is a nucleophile. Halogenoalkane undertakes partial hydrolysis with water molecules in the nucleophilic substitution. And finally, acid chloride easily undertakes complete hydrolysis, which is a nucleophilic substitution in the presence of water. With that comparison done, let's now study acid chloride. Firstly, acid chloride is not an acid, because if you look at the structure, it is not a proton donor, as it doesn't have any proton that is actually electron deficient, highly protonic. Second of all, is that acid chloride easily undertakes nucleophilic substitution, and the Cl is an excellent leaving group, given the extremely weak bond energy between C to Cl. So let's take a look at some of the reactions that it can undertake. So in the first reaction is that it reacts with water molecules to actually produce carboxylic acid. That occurs spontaneously, and the process they produce hydrochloric acid, which is actually a strong acid. So therefore, if you actually have an acid chloride with water, if you have an acid chloride aqueous, it will chemically alter itself to form a carboxylic acid and hydrochloric acid. In the presence of ammonia, it can undertake nucleophilic substitution again to actually produce amide. And the byproduct produced is now HCl. In the presence of primary amide, it will also be able to undertake the reactions to produce now a secondary amide. And needless to mention that if you use a secondary amide, for example, with 2R group bonded to N, then you will end up with actually a tertiary amide. Finally, it will react with alcohol to produce your ester, and it will also react with phenol also to produce the ester as well. And at times in all these reactions, you will find that pyridine is being added to remove the copious amount of hydrogen chloride gas that's produced. And those gases are in fact toxic and acidic. So by adding that, they actually remove it by forming an ionic compound. So this is your pyridine. Pyridine has a molecular formula C5H5N. You'll see that later when we get on to nitrogen, we'll discuss that a bit further, and we'll talk more about it. So in conclusion, acid chloride is capable of reacting with water molecules to produce carboxylic acid, with alcohol and phenol to produce ester, with ammonia to produce amide, and to react with primary or secondary alcohol to produce your secondary or tertiary amide. And all of them will actually release the byproduct HCl. And let's take a look at an example. Let's study the compound now that which of them will be more easily hydrolyzed. Certainly your acid chloride will hydrolyze the most easily, and relative to that, and it will be followed by halogenal alkane, and more specifically your bromoalkane, because the Br is much bigger, so the CBr bond is weaker. So this will hydrolyze the most easily, followed by this, and then this. Why does this hydrolyze the slowest actually? Because it bears resemblance to that of your chlorobenzene. In the case of chlorobenzene, we mentioned that this bond energy is partial double covalent bond because the p electron overlaps with the delocalized pi electron in the benzene ring. In this case, one need to bear in mind there will be some form of conjugation as well. So the conjugation that occurs is because, again, the lone pair electron in chlorine could actually overlap pi electrons in C to C double bond because they all actually sit on the same plane. Specifically, chlorine and carbon atoms all sits on the same plane. So therefore, because of that, there will be some partial double covalent bond character between C to Cl in the case of this compound T, and hence because of this, it is least able to undertake hydrolysis in the presence of water.